Okay, good afternoon. What don't you think so, Armando? Sorry, you guys are interrupting my ice cream break. So, got mint chip ice cream here. So just, I don't want it to melt. It's the only thing in life that brings me happiness is my mint chip ice cream. Priorities, exactly. Exactly. This is our class mascot. So this is our class mascot. Hello, sir. His name is Buster. Buster, aka Slasher, aka Cujo. Okay, he will rip your face off. Okay, but he's nice to me. So he's our class mascot. Okay, let's get to work, shall we? I gotta take another bite of my ice cream. There we go. That's good stuff. Okay, any questions on anything up to this point? Gosh, we've only met once so far, right? So this is our second time. I'm really liking the fact that a lot of you are utilizing the Pronto. Oh, is it Pronto? What is this? Yeah, Pronto, right? No? Yeah, Pronto, yeah. Okay, the Pronto, so I've fielded a couple of questions there. So as you can tell, I'm up pretty late at night every night. I'm a night owl. So the problem is I have to wake up at like 8 in the morning. So it's not my favorite, but I usually go to bed around 1 or 2 in the morning. So, but anyway. Okay, so vectors. Let's talk more about vectors today. Shall we? Let's get into it. Let's get into the vectors. Okay. So let me share my screen real quick. Okay, let me add a page here. Hey, Pedro, can you mute yourself, please?
Yes, I can hear you.
Yeah, can you mute yourself, please? Mute.
Yeah. What did you say?
Never mind, forget it. I'm gonna mute you because it's just distracting to hear you go in and out of your car. So I'm gonna add a page here. I need to insert some blank pages here. Okay. While that's loading, I'm gonna have some more of my ice cream because it's hot out. When did Southern California turn into like the surface of the sun? That's all I want to know.
About 2 weeks ago, apparently.
Like, forget. I'm like, right, go move by the beach. It'll be nice and temperate climate. They lied. They're liars. It's hot. It's hot as hell. Maybe not that hot. Okay. Okay, we got my blank document up. That's good. Get this guy out of the way. Perfect. Bring you up. Huh? This is going to be 12.3 and 12.4. Okay, perfect. Okay, let's get into talking about the dot product and the cross product. Dot product and cross product today. Okay, the dot product. Okay, if A is equal to A1, A2, A3, and B, vector B, is equal to B1, B2, B3, then the dot product of A and B dot. Okay, of A and B is the number given by A dot B, where A dot B is equal to A1 times B1 plus A2 times B2 plus A3 times B3. Notice that this thing is no longer a vector. This is a scalar, we call it. This is just a number. It's a scalar. This is a number. This dot product turns vectors into scalars. This A was a vector, this B is a vector, but it turns it into a number. It's a scalar. Okay? It's a scalar value. We're multiplying the components together and then adding them. Okay, we multiply the X components, the Y components, and the Z components all together, and then add them, take their sum. That's the dot product. Okay, this is also called the scalar product or inner product. Okay, also called the scalar product or the inner product. Okay, since a scalar is produced. Okay, number one. Okay. Okay, 2, 4. Dot 3, negative 1. Okay, we're going to take 2, 4 and we're going to dot it with 3, negative 1. Okay, so what's this going to be? This is going to be 2 times 3. Multiply the first components together and add times the product of the second components. Okay, so this is going to be 6 minus 4, which is 2. Okay, B, let's try one in 3 dimensions. Negative 1, 7, 4, dotted with 6 to negative 1/2. 6 to negative 1/2. This is going to be negative 1 times 6 plus 7 times 2 plus 4 times negative 1/2. What's that going to be equal to? This is negative 6 plus 14, okay, minus 2. So that's going to be 14 minus 8, which is 6. Positive 6. Okay, letter C. Let's say that we have it in standard basis form, I plus 2j minus 3k dotted with 2k or 2j, this thing dotted with 2j minus k. Okay. So you could turn this into component form if you really wanted to, and then dot it, or you could just, dot it by looking at the first components here, except there is no first component. That would be 0, right? You would think of it as 0. So if you want to look at this in component form, this would be 1, 2, negative 3, dotted with 0, 2, because 2 goes with j. J is y, not x. And then this is negative 1, right? And you could dot this. 1 times 0 is 0. So that's 0. 2 times 2, 4. Oops, this is a scalar. Sorry. 0 plus 4. Okay, and then negative 3 times negative 1, that's positive 3. So this thing becomes positive 7. Okay, that's the dot product for that one. Okay, let's look at some properties of the dot product. Okay, properties of the dot product. Okay, 1. Okay, A dot A. What happens if I take a vector and dot it by itself? A dot A. It's kind of interesting. Let's think about this for a second. A dot A. Well, let's let A be. Let's let A be X, Y, Z. Okay. Let's dot this. Let's dot this with itself. Okay. So let's do X, Y, Z dotted with X, Y, Z. So what's that going to be? That's going to be X squared plus Y squared plus Z squared. Huh, that's interesting. X squared plus Y squared plus Z squared. Okay. Which, if you think about the magnitude of A, how did we get the magnitude of A before? The magnitude of A was the square root of X squared plus Y squared plus Z squared. Oh, okay. But this just doesn't have a square root. So I could square both sides. And this thing ends up being the absolute value of A squared. So that's property 1. Property 2. Okay, is A dotted with B plus C, vector B plus C. Now, these are all vectors. Okay, lowercase c is a vector. Okay, so this is equal to A dotted with B plus A dotted with C. So it's kind of like the distributive property for dot product. Okay, so distributive property for dot product. Kind of the way it works. Okay, what about number 3? Number 3, A dot B is equal to B dot A. It just means that multiplication is commutative, and so is multiplication is commutative, okay, and so is the dot product. Okay? And so you can dot in any order, and it retains the same. So this is the commutative dot property. Okay. You can dot in any order because multiplication and addition are the only properties here, and you can multiply and divide in any order. Okay, number 4. Okay, number 4. We're going to say that what would be a good letter here? Let's do M. M dotted with A, or sorry, times A, M times A, okay, dotted with B. Okay, now A is a vector, B is a vector, but M is a scalar. Okay, so M is a scalar. It's just a number. M is a scalar. Okay, but this guy is the same as M times A dot B. Okay, which is the same as A dotted with MB. Just says, look, I can put the scalar anywhere, and it's the same thing. Okay. Does that make sense? Okay, it's kind of like, I don't know what it's like, but kind of like some sort of associative property for dot product. Okay, number 5. Okay, last property. Okay, 0 vector, the 0 vector dotted with A is equal to 0. Okay, 0. The 0 vector dotted with A is equal to 0. And what does that mean? What's the 0 vector? Well, it's just the vector full of zeros. That's what the 0 vector is. Okay? So let's think about this for a second. If I take 0 vector and dot that with A, well, what am I going to get? Am I going to get 0 plus 0 plus 0? And what's 0 plus 0 plus 0? Well, that's 0. Okay. Let's take a theorem here for the dot product. Theorem, if theta is the angle between the vectors A and B, okay, if theta is the angle between the vectors A and B, then A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. Okay. Okay. And the proof of this comes from the law of cosines. I'm not going to get into a lot of that here, okay, but the law of cosines, okay, a minus b magnitude squared is equal to the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times the cosine of theta, okay, for this triangle. What triangle am I looking at? For the law of cosines, I'm looking at this triangle here. Sorry, not that one. This triangle here, AB and the angle between, right? AB and the angle between. So if I wanted the vector that creates the third side here, this would be vector A minus B. And we went over that on Monday, why that is. Okay, remember that the diagonal there of the parallelogram would be A plus B, but the other diagonal, the one that connects the two vectors head to head, okay, is A minus B, okay? So if we use the law of cosines here, okay, we could easily derive this identity here, okay? Why? How could we easily derive that identity? Well, we would get, okay, the magnitude of A minus B squared, okay, minus the magnitude of A squared minus the magnitude of B squared, right, okay, is equal to negative 2 times the magnitude of A, magnitude of B cosine theta. Okay. So let me divide by the negative 2 here. Or actually, let's just divide by the negative. And I'm going to say that this is A squared minus, well, let me think about this for a second. This is plus magnitude of B squared minus A minus B squared is equal to negative 2 magnitude A magnitude B cosine of theta. Okay. Oh, the negative is gone. Sorry, I distributed the negative through. Okay, so what does this look like? Oh, this guy, I'm gonna write it as this. I'm gonna say this is A1 squared plus A2 squared plus A3 squared, right? That's what the magnitude of A squared is, okay? Plus, this is going to be 1 squared plus B2 squared plus B3 squared. Okay, that's interesting. Minus, okay, the magnitude of A minus B, okay, squared. So this is going to be A1 minus B1 squared plus A2 minus B2 squared plus A3 minus B3 squared. Interesting. Okay. Is equal to 2 times AB cosine theta. So let's see what we get over here. We multiply this out. We get a A1 squared plus A2 squared plus A3 squared plus B1 squared plus B2 squared plus B3 squared. This is going to be minus, okay, A1 squared minus 2AB, A1, B1, minus b1 squared. Oh no, it's plus, sorry, plus b1 squared. Okay, and then this is going to be plus a2 squared minus 2a2b2 plus b2 squared. And then this is going to be plus a3 squared minus 2a3b3 plus b3 squared. Okay, and that equals this thing above. This thing running out of space. Okay, that's what it equals that above. Okay, just bring that right down. This is 2 absolute value A, absolute value B, cosine of theta. Okay, so let's distribute the negative sign here. What are we going to get? Well, can you see that when I distribute the negative sign, all of these are going to go negative? Right? All of those are going to go negative when I distribute the negative sign. And all of these are going to turn positive. Right? That equals 2 A B cosine of theta. Now, why am I getting rid of all this stuff? Isn't that going to cancel? Oh yeah, that's going to cancel. That's kind of cool. So what happens if I divide by 2? I just get that. But what is A1B1 plus A2B2 plus A3B3? What does that equal? What does this thing equal?
Vector A times vector B.
Times?
The dot of A and B.
It's A dot B. That's what that is, right? Isn't that A dot B?
Should it be vector A times vector B? If you put A times B, it doesn't mean anything, right? Because I took it from physics.
Say that again?
Should it be vector A times vector B? Since I took it from physics last summer, and it should be 2 vectors multiplying.
There's no
Right.
vector multiplication.
Uh,
It's called the dot product or the cross product. So what are you talking about here? Are you talking about the dot product or the cross product?
a dot product. So you're saying A times B gonna be the magnitude of A times magnitude of B cosine theta?
Well, no, what I'm saying is this equals the dot product of A dot B. And yes, those are vectors. Does that make sense? A and B are vectors. We've already established that A and B are vectors. Okay, A is this vector. A is the vector A1, A2, A3. Those are components. B is this vector. B1, B2, B3. Does it make sense? We've already established that these are vectors.
Yeah, but what I was saying, why don't you put the vector sign on it so it will create less confusion?
Oh, it would create less confusion if I do this?
Yeah.
Okay, go ahead. If you want to put that, okay, the reason I don't do that is because, you know, we've already established that A and B are vectors. Okay, if they have subs, then they're components of that vector. Okay, the other thing that I don't do because I don't want to sit there and spend so much time is I really could go like this. I really could what do I want to do here? No, I don't want that. I want my other stuff. Here we go. Stop. Stop. Stop it. Stop it. Stop it. Stop. Go away. Okay. Nope. Come back. Okay. I could really go like this. but I don't really want to. I don't really want to take the time to always do this, okay? I could say, this is vector AB. Now, how am I going to represent vector A times vector B? I could do this. I could be like vector A dotted with vector B because it's bold now. But I don't want to take the time to do that. Okay, but we already established that these two are vectors, then they're vectors. Does that make sense? Okay, if they're bold, then they're vectors. Okay, but I don't want to spend the time on that. And I think you're going to figure it out after we do this for an entire semester. Okay, because we're going to be using vectors for the entire semester, and you're gonna know which ones are components and which ones are vectors really quick. Okay, and I'm sorry that this isn't a physics class. It is kind of. This is a pre-engineering class, so hopefully you're able to adapt to the notation. Okay, does that make sense? And my screen just went blurry for some reason. Let me stop the sharing and we'll go back to share it again. Okay. Hopefully that's a little clearer. Okay. Are we good? Are we all good? We good? All I'm doing is deriving this formula anyway. So the formula is, okay, A dot B is equal to magnitude A, magnitude B times cosine of theta. Okay. I mean, the book.
That was easy.
It was easy.
That was easy.
Yes, I got you. Okay, thank you. It was easy. It was very easy. This calculus is easy. Okay, that's the idea behind this. So let's go to the Bible. Okay. Let's see what the Bible says. Okay. So, yes. Okay. So, if we look at the Bible here, okay, I don't know if you can see this or not. Okay, this is the calculus Bible. Okay, do you see how the text has the privilege of bolding everything? Because they can put it in bold every time to make it a vector. You're just going to have to assume that these are vectors, okay, when I write them out. Does that make sense? Yes, they're bold. They're in bold typeface. But I'm not going to sit there every single time and write in bold typeface for it. Does that make sense? Yes? No? Are we good? Hopefully we're good.
Yes, we are good. We're good. We're good.
Thank you. Thank you, Pedro. We're good. Oh, okay. Yay. Now we can use this formula. Okay. How do we use this formula? Well, this formula is actually going to give us the angle between two vectors. The angle between two vectors is really the inverse cosine of A dot B over the magnitude of A times the magnitude of B. Okay, so that's the angle between two vectors, is the inverse cosine, okay, of okay, and this is going to be an angle from 0 to pi. So this is from 0, okay, to pi. Why? Why is this an angle from 0 to pi? Any ideas? Why would it have to be an angle from 0 to pi? Well, what's the largest angle that two vectors could make?
180.
Yeah, how about pi? Right? How about pi? Isn't that the biggest angle that two vectors could make is pi? So it makes sense that the inverse cosine here would go from 0 to pi, and it does. Okay? It all works out. Okay. So okay, let's do an example here. If A and B, okay, have lengths 4 and 6, and the angle between them is pi over 3, find A dot B. Okay, find A dot B. Okay, what's A dot B? Well, A dot B is equal to the magnitude of A times the magnitude of B times the cosine of theta. Well, this is easy. A dot B is equal to 4, that's the magnitude of A, times 6, that's the magnitude of B, okay, and times the cosine of pi over 3. Well, what's the cosine of pi over 3? Not everybody at once.
1/2.
Thank you, Armando. Yes, 1/2. The cosine of pi over 3 is 1/2. So we want half of 24, which is 12. Okay, so A dot B is equal to 12. Okay. So that's kind of cool, right? So the dot product is equal to 12. Okay, so nice, nice, nice. I like what I've done there. Yes. Okay, number 3. Find the angle between vectors A, which is 2, 2, -1, and vector B, which is 5, -3, and 2. Okay, 5, -3, and 2. Okay. So what do we need?
Need the magnitude of A and B.
Okay, oh, we need the magnitude of A and B. We also need to know what the dot product is, right?
Yeah.
Who said that? Pedro?
Yes.
No, it was me, Hung.
Oh, Hung. Okay, thank you, Hung. Okay, so yeah, we need all of those. We need to know what is A dot B, right? So the cosine theta is the inverse cosine of A dot B over the magnitude of A, magnitude of B. Okay. So theta is equal to the inverse cosine of, okay, so what's A dot B here? What's A dot B? That's going to be 2 times 5, which is 10, 2 times -3, that's -6, and -1 times 2, that's -2. So this should be equal to 2, right? A dot B is equal to 2. Okay, so that's 2. Okay, what's the magnitude of A? What's the magnitude of A? Well, isn't that just 2 squared plus 2 squared plus -1 squared square root? So what is that? Isn't that the square root of 9, which is 3? Right? Okay, so that's 3. And then we're going to multiply by the magnitude of B. What's the magnitude of B here? Well, that's 5 squared, okay, plus -3 squared plus 2 squared. Okay, so that's 25 plus 9 is 34, plus 4 is 39. I'm sorry, 38. So 34 plus 38, 34 plus 4 is 38. So this is the square root of 38. So this is radical 38. So theta is going to be equal to the inverse cosine of this. We're going to find out what theta is. What's theta here? Stop my sharing for a second. Okay. So I'm going to go inverse cosine. I need to make sure it's in radians mode. Are we in radians mode? Yes. Good. Okay, so I'm going to go inverse cosine. Okay, inverse cosine of, what did we want? We want the inverse cosine of 2 over 3 radical 38 of 2 divided by 3 times the square root of 38. Parentheses, close parentheses, and enter. And I'm getting about 1.462 radians. 1.462 radians. What's that in degrees?
71.1 degree.
Let's see. Let's multiply this by 180 over pi, right? I'm getting 83.4. Or sorry, 83.8 degrees.
Yes, I agree.
Okay, perfect. So this is going to be 83.8. Is that right?
Yeah.
83.8 degrees. Okay. Okay. Two vectors are orthogonal, okay, if and only if A dot B is equal to 0. A dot B is equal to 0. Okay, two vectors are orthogonal if A dot B is equal to 0. IFF. Let's talk about a couple things that are going on here. What does IFF mean? If and only if. Okay, this is a biconditional statement, biconditional. Okay, it's arrows in both directions. If and only if. Okay, means if one, then the other. If the other, then the one. Biconditional, goes both ways. Okay, it's basically, if you have a definition, that's biconditional statement. An equilateral triangle, if it's equiangular. It's an equiangular triangle if it's equilateral. That's a biconditional statement. So I could say that a triangle is equiangular if and only if it is equilateral. A triangle is equilateral if and only if it is equiangular. Okay. What does orthogonal mean? Anybody know what orthogonal means?
Perpendicular.
90 degrees.
What is it?
Perpendicular.
Perpendicular. Yeah, it's just a fancy way of perpendicular. Perpendicular. Okay, it's just a fancy name for perpendicular. So two vectors are perpendicular if and only if their dot product is 0. This is very important, very powerful. Two vectors are orthogonal if and only if their dot product is 0. A dot B equals 0. Okay? If their dot product is 0, then they are orthogonal. Okay. So the angle between them is what? What's the angle of two orthogonal vectors?
90 degrees.
Yeah, is there a way to prove that? Is there a way to prove that? What's the inverse cosine of 0? What's the inverse cosine?
90.
Of 0, right? Inverse cosine is pi over 2. So, does that make sense? That's where we get this from. If we're taking the inverse cosine of 0, then that must mean that we would have a 0 in the numerator. Why would there be a 0 in the numerator and not the denominator? Well, because we can't divide by 0. It's not allowed. It's fundamentally flawed in mathematics. And therefore, 0 must have been in the numerator, which means A dot B must have equaled 0. Therefore, these vectors were orthogonal. Oh, okay, that's cool. Okay, so if A dot B is equal to 0, okay, then they're orthogonal, or the angle between them is pi over 2. What if it's less than pi over 2? Then the angle is what?
Acute.
Yeah, it's acute. It's a cute little angle. Okay? It's acute. If A dot B is less than, okay, what am I trying to say here? If A dot B, the inverse cosine, let me think about this for a second. If A dot B, okay, so the only thing that's changing here is the angle, right? Let's think about this for a second. Here we've got theta, here we've got A, and here we've got B, right? Okay. So we know that if it's 0, right? If it's 0, okay, then this thing is pi over 2. But what if it's positive number? What if this is a positive number? What happens when we take the inverse cosine of a positive number? What type of angle is that? What's the inverse cosine of a positive number?
It's an acute angle.
Yeah, it's in quadrant 1, isn't it? Does that make sense? It's in quadrant 1. Right? The inverse cosines are positive in quadrant 1, and so this is an acute angle. So if A dot B is greater than 0, then theta is acute. Okay? If A dot B is greater than 0, if it's positive, it's acute. What happens if it's in the second quadrant? What if A is now over here? Then it's obtuse, right? What would A dot B? What are the cosine values over here in the second quadrant? What are cosines? Aren't they negative?
Yes.
The cosines are negative. So if we want to take the arc cosine of a negative value, right? So the arc cosine of a negative value, okay, then A dot B would be less than 0, right? Then theta is obtuse. Okay, so it's kind of reverse of what you would, think intuitively, right? Okay, directional angles. The directional angles, okay, of a vector are the angles alpha, beta, and gamma. Okay, alpha, beta, gamma. Okay, so that's an alpha, by the way. Okay, that a vector makes with the positive x, positive y, and positive z axis are the angles. Okay, the directional angles of a vector are the angles alpha, beta, gamma that a vector makes with the positive x, y, and z axis. The positive x-axis, x, y, and z axes. Okay, and I'm pretty sure that, where's my files here? Okay, so let me go to my documents. What's this, 280? PowerPoint, let's go to Stuart, PowerPoint. What are we on, 12.3? Okay, this guy draws a much better picture than I could ever draw. So, let's see what we got here, the dot product. Blah, blah, blah. We went over that already. We went over this, that's good. Yep, good, 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 okay, blah, blah, blah. Our dot product, okay. Directional angles, here we go. Directional angles. Is there a picture? Yes, here we go. There's the picture that I would have a really hard time drawing. Okay, so there's our vector that's kind of coming out at you, right? This vector is kind of coming out at you, right? And so what's alpha? Alpha is the angle that makes in the x direction. Beta is the angle that it makes in the y direction. And gamma is the angle that it makes with the z direction. Okay, so just kind of think of it like that. Okay, can I draw on this? Can I draw on this? So it really is more like a projection. Okay. It's the vectors that the angle makes with the positive, yeah, it's the angle that the vector makes with the positive x-axis, the positive y-axis, and the positive z-axis. So this is good. It's a fine drawing. Okay, so it's not a projection. A projection would be this. Okay, if I had my vector, let me get rid of that. If I had my vector, okay, and I wanted to project this vector onto the xy plane, okay, then what I would get is I would get an image of this vector onto the xy plane. I would get an image of this vector onto the xy plane. And then this would be the angle projected, right? That angle is not alpha. Okay, it's not alpha. Okay, what the angle is it's the whole angle in space, in 3 space, that it's kind of lifting off the xy plane, and that creates alpha there. Okay, so not alpha, not alpha. This one is the projection. This is the angle theta projected onto the xy plane. So just don't make that mistake. They're different angles, if that makes sense. Hopefully makes a little bit of sense. Okay. Okay. So yeah. Let me get rid of this. Let's go back to the notes. Okay. So the cosine of alpha, if we have a vector A, which is A1, A2, and A3, right? Okay, that's my vector. Okay, and again, I'm not gonna do this every time because it's gonna be a pain. But if Hong really wants it, just go ahead and put that as a bold A. Okay, Hong? Go ahead and do that. If you need that for your own sanity, you're good. Okay, but vector A has these components, right? And alpha, beta, gamma are the angles. right, are the angles, okay, in three-dimensional space. Okay, you have to start thinking three-dimensionally in this class. Okay, that's what kind of separates those who can do the engineering from those who can't, is can you visualize the bridge in three-dimensional space? Can you visualize it and how it's going to how this building is going to sway, or can you visualize that in your mind? Okay, I keep saying engineers, but is there anybody in here that's not an engineer, not an engineering major?
I'm not.
I'm not.
What's your major?
Math.
Oh, math. Okay, well that's good. That's awesome. That was my major too. Okay. You're also math. Armando's math? Okay, that's cool. Anybody a computer science major? No, they're done. Anyone biology? Physics? Okay, physics. There you go. That's good. Yes, good. Okay. So what's your major, Hung?
I'm a physics major.
You're a physics major. Okay, that's good. Okay, that makes a lot of sense. Why you're a physics major. That's good. Okay. So yeah. So that physics notation is a little bit different, and engineering notation is a lot different than the mathematics notation that we have, okay? So just keep that in mind. You're gonna have to learn all three notations. Okay? So there are certain nuances that we do in different courses. Okay. And when we get there, I'll discuss that as well. Okay, but if you're a physics, if you're engineering, physics, or math major, you're in the right place. Okay. So, but again, I teach this from a math major's perspective, not an engineering major's perspective or a physics major's perspective. Okay. Now, when we get into chapter 16, it's all physics. So I'll switch hats. I'll take one hat off and put the other one on. Okay. But the calculus books are written in a math major's perspective. Why? Because they're written by all mathematicians, right? Does that make sense?
Yeah.
They're written by mathematicians. So goes to be understood that it's from a mathematician's perspective. Right? So just, we're just broadening our horizons here. I used to do engineering. I did material science engineering for a couple of years, and then I went into teaching. So I didn't really like the material science engineering. I was just building capacitors and superconductive capacitors, and I just wasn't happy with it. So I went into teaching math. Got out of engineering. So I still have some of those friends from engineering, and met one of them, and they said, "Oh, look at this grain boundary layer semiconductive material that we found, and this is what I built last year, and it was put into the new iPhone. What is it? What are we on now? Not iPhone 17, something like that. I don't know. Generation 200." And he's like, "See what I built, Jason?" He's like, "See what I built last year?" And he turned to me and he was kind of a jerk about it. He said, "What did you build?" And I thought about it for a second, and you know what I told him? I said, "I built engineers." I kind of shut him up for a second. So anyway, true story. Okay, cosine of alpha is going to be A1, the first component of A, over the magnitude of A, the cosine of beta is equal to A2 over the magnitude of A, and the cosine of gamma is equal to A3 over the magnitude of A. Okay, number 5, find the directional angles, alpha, beta, gamma, of A. Okay, so we have 1, 2, 3 in space here. Okay, so if A is equal to 1, 2, 3 in 3 space, then what are alpha, beta, gamma? Okay, then what are alpha, beta, gamma? Let me just play around with something real quick. I don't know if this is going to work or not, but I just want to see. Okay, so let's see what happens here when I do my 3D calculator. Do I want this? No, I don't want that one. What do I want? I want the other one. I want, is this one going to work for me? No, that's my parametric grapher as well. I just wanted a vector in 3 space. Will this graph just a vector? I don't know. Draw display window. I don't want it to be animated. Turn the animation off. Okay, what's function A here? Okay, so x of t. Oh, I think this will do it for me. Okay, x of t is going to be, where's my controls? Go. Okay, so let's just go over. Yeah. This is gonna work. Okay, turn the freaking animation off. I don't want the animation. Okay. Whatever. Function B. Oh, more settings. There we go. Position vector. I want that. Oh, animate. Turn the animation off. There we go. Like, stop, bro. Just stop it. Okay. So now we're going to go here. We're going to say the x component of this vector is 1. Okay. The y component of this vector is 2. And the z component of this vector is 3. Okay. Stop. Go away. Okay. Enter. Okay. So what is this going to look like? Can I rotate this? No. I thought I could at one point. Oh, there we go. Let's rotate this. Rotating. Okay. So, and then what do I want t to be? Nothing. I want t to be nothing. Okay. I want t to be 0. Okay. So, is this going to give me the proper, what's the scale that I want here? 0. Okay. Okay. So position vector, yes. Okay, let's see what we got here. Okay. So x of t, y of t, z of t functions. Why is that not liking what I'm doing? I want it to be out at 1, 2, and 3. Maybe this isn't going to do it for me, unless I'm doing something wrong. Okay, let's go back to the animation, I guess. What am I doing wrong here? Why is it saying that x is 0? Oh, I know why. Because I made t max to be 0. What do I want here? Go. Oh, I know what I'm doing wrong. I know what I'm doing wrong. Okay, I'm put some t's in here. 1t, 2t, and 3t. Okay, and then what do I want t min to go from? I want it to go from 1 to 1. 1 to 1. There we go. Now where are we at? Okay, now we're at the right spot. Now we're at the right spot. Now we're playing with gas. Now we're playing with fire. Okay, so that should be right. Should be right. I think. Okay, so T min is going from 1 to T max is 1. Anyway, I don't know if this is going to give me what I want, but it's good. It's a good try. 0 to 2 pi. I don't know. There should be a better one here. Okay. Let's go to a vector grapher. Okay. 3D vector plotter. Desmos. It's in Desmos. That's nice. 3D vector plotter. Okay. Ah, here's the vectors. Nice. Okay, that's cool. That's what I wanted. Okay. So vector V. Okay, I just want. Is this going to allow me to edit? Yeah. Okay, vector V. I just want 1, 2, 3. Okay, for my vectors. Vector V. Vector 2, I don't want. Show resultant vector. Oh, this shows the resultant. This shows the difference. It's a good one. You should probably bookmark this one. Okay, this is kind of cool. So show the dot product, show the difference, show the cross product. That's cool. If I had 2 vectors, I could show the cross product. Oh, that's kind of cool. Okay, so just make them both the same. Okay, so here is the vector that we're working with. I can move it to the right spot. You can see. Okay, so at any rate, there's a lot of different 3D graphing software out there for free. So just choose one that you like. This one's a good one. I'm gonna bookmark this one. Yeah, this to my bookmarks. Okay, so this is just your 3D plotting. So your X's, and then your Y's, and then your Z's, right? So X's, Y's, and Z's. So here we go. Boom, just like that. Okay, and then your Y's. Okay, so if I wanted to do the X's and the Y's, the Z is coming out at me right now. Okay, so I didn't really like this, but XY, yeah, that's the XY plane. That's correct. Yeah, it's cool. Anyway, enough wasting time with this guy. But you get the idea. This is our vector here. Boom, X, Y, Z, right? Boom, that's our vector 1, 2, 3. Okay, so the angle, so I can't really write on this, but the angle, okay, that it's going to make with the X axis is going to be alpha, right? So what's alpha? Alpha is the inverse cosine of A1, which is 1 over the magnitude of this. So what's the magnitude of this? 1, 2, 3. Well, that's just 1 squared plus 2 squared plus 3 squared, which is 14. So this is the inverse cosine of 1 over 14. Okay, which is approximately 74 degrees. Okay, 74 degrees. Okay, beta is the inverse cosine of 2 over radical 14, which is approximately 58 degrees. And gamma is the inverse cosine of 3 over radical 14, which is approximately 37 degrees. Okay, so that's how we do that. Okay, so dun, 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 dun. Okay, a wagon is pulled. I don't know what number we're on, but whatever. We're on number 6? Yeah, we're on number 6, right? Okay, so number 6. Okay, a wagon is pulled a distance of 100 meters along the horizontal by a constant force of 70 newtons, okay, applied to the handle at a 35-degree angle. The 35-degree angle. Find the work done. Okay, so work is force over distance, right? Force over distance. Okay, that's the work. The work is the force over distance. Okay, and so we actually have, okay, a formula for this. The work is actually the force dotted with the distance. Okay, the work is the force dotted with the distance. Okay, so this is going to be equal to the magnitude of the force times the magnitude of the distance times the cosine of the angle between them. Okay, so what is the work done here? The work done is going to be equal to the magnitude of the force. Well, the magnitude of the force is 70 newtons. Okay, and the distance is 100 meters. Okay, and that is being applied at an angle of 35 degrees. If I plug this into a calculator, I'm going to come out with 5,734 what? 5,734 what?
Newton meters.
No, it's not Newton meters. What's a Newton meter? Come on, Hong. What's a Newton meter?
It's joule.
It's a joule, exactly. It's a joule. Okay, it's a joule. Thank you. Okay. Okay, let's go on to cross product. Okay, cross product. What's the cross product? Okay, A cross B can be represented as A2B3. Okay, if you have your components, right? A is equal to A1, B1, or sorry, A1, yeah, B1, C1. No, sorry. A1, A2, A3, okay, and B is equal to B1, B2, B3. Okay, then this thing is going to be, A cross B is A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, A1B2 minus A2B1. Okay, now notice that the cross product is a vector. It's a vector. Okay, and A cross B will always be orthogonal to both A and B. Okay, so let me say that again. A cross B is orthogonal to both A and B. So if I have, okay, here, if I have vector A and vector B in the XY plane, vector A and vector B, okay, and hung, just know their vectors, right? Everybody should just know their vectors. They said they're vectors. Okay, if you want to bold them, you can. If you want to go like this, you can. Doesn't matter. Okay, can I go up a bit? Sure. There you go. Okay, and so where's A cross B? Well, A cross B, okay, is going to end up here. This is A cross B. Remember that right-hand rule? Right, remember that right-hand rule? A cross B, we're going to use that here as well. A cross B, right-hand rule. Okay, so they're orthogonal. Okay, they're orthogonal to both A and B. So A cross B is orthogonal to both A and B. Okay. Okay, right-hand rule. Okay, so the way that we can rewrite this thing without having to memorize it every time is we say that A cross B is equal to the determinant of the following matrix. It's I, J, K. Okay, I'm just kidding. No, I'm not. Sorry.
Actually, I have this from the notes that I took in summer of physics. It's about the cross multiply. Yeah. Oh, actually, you got it.
Okay, thanks. Okay, IJK, this is A1, A2, A3, B1, B2, B3. When we find the determinant of this matrix, we get the exact same thing that we had above. Okay, to find the ith term, we cross off the first row and the first column, and we say that this is going to be the determinant of A2, A3. These are called the minors or the cofactors. Okay, and then B2, B3, I. Okay, minus, remember it goes plus, minus, plus when you do matrices, right? So this is minus the determinant of A1, A3, B1, B3, J, plus the determinant of A1, A2, B1, B2, K. So as you can see that this is going to give me the exact same thing we got before. A2, B3 minus A3, B2, I, which is my first component. Okay, and then, you know, subsequently, it's going to get the same thing. Now this negative is going to reverse things. So this is really going to be A3, B1 minus A1, B3. Okay, and then this thing is going to stay A1, B2 minus A2, B1. Right? Does that make sense? What's the image you got here, bro?
Actually, the same that you are writing.
I don't want it in my system. I want it on my desktop. Save. And file. What you got for us? Okay. The cross product is this. Okay, perfect. Awesome. Thank you. Yes. Perfect. Okay. So nice. Okay. So let's do example 1 here. Okay, let's find A cross B if, okay, A is equal to 1, 3, 4, okay, and B is equal to 2, 7, negative 5. Now remember, not everybody in here is an engineering major, and not everybody in here is a physics major. So we don't all come in with the same prerequisite knowledge. So we have to just make sure that everybody's on the same page. Okay? Just because you know something doesn't necessarily mean your neighbor in the class already knows it as well. Okay, so I had to learn that myself in school. I was very, I don't know what you call it, self-focused. Okay. So it even led my the self-focus even led into my teaching career. I was teaching high school, and in my 3rd year of teaching, I was ready to give up teaching. I was like, I'm done. I'm done teaching high school forever. Okay, I now teach college, but I did teach high school for another 12 years after that. And I was very frustrated with teaching high school. And I came home one day to my wife and I said, I'm quitting. I'm done. She says, okay, what are you going to do? I'm like, I don't know, maybe go back to engineering or do something else. And she says, well, why are you quitting? Why are you quitting teaching high school after just doing it for 3 years? I turned to her and I said, it's because these kids are so freaking stupid. They're so dumb. I don't know how they tie their shoes in the morning. So they're just complete morons. And she turned to me and she says, okay, I understand your frustration. And she said, you got it all wrong though. I said, what are you talking about? She says, you're so self-absorbed. You're so self-centered. I said, what do you mean? She says, you really think that this is all about you, don't you? I said, I still don't understand what you mean. She said, Jason, all of your life, you've been striving to be number 1. She says, all of your life, you graduated from high school with honors. They gave you a gold sash. You then graduated college with honors. They gave you a medal. I still have that medal. I should probably throw it away. But they gave me this academic medal when I graduated with my bachelor's degree with honors. Magna cum laude, summa cum laude. Thank the Lord. Just kidding. She says, you've been striving for this academic excellence to prove that you are someone in this world. She says, you have it all wrong, though. She says, you became a teacher. She says, the moment you step foot in that classroom, it became nothing about you. It became everything about what you can do for those individuals. She says, if you're expecting to get something out of this, then you should quit today. But if you're expecting to give something into this, then you should stay for a lifetime. She says, you've been climbing this mountain of academic excellence and performance for your entire life so that you could be number 1. And she says, it's awfully lonely on top of that mountain, isn't it? Looking down at all these idiots that you have to teach. She says, you have the completely wrong perspective. She says, your job isn't to get to the finish line first. Your job is to make sure that there are as many people there with you. And that day changed my entire perspective about what my career was. Because in that moment, it no longer became about everything that I had accomplished. Who cares? It was about everything that I did to better myself so that I could better those around me. See, that day I stopped teaching math and I started teaching people. And it has made all the difference in the 20 plus years of my career. So again, I used to be very, very self-focused. I try not to be that anymore. I try to get out of that mentality. Anyway, I just thought I'd share. Thank you. Okay, let's do this one. Let's find the cross product. Okay, A cross B is equal to IJK. Okay, I'm just kidding. Okay, 1, 3, 4. My wife is very wise. She was very wise. She was very wise for a 26-year-old lady. Okay. That's why she's still my wife. Okay. Anyway. Okay, 2, 7, and -5. Okay. 2, 7, and -5. Okay, let's find the determinant of this matrix. A cross B is equal to, okay, the determinant of 3, 4, 7, -5, I, minus the determinant of 1, 4, 2, -5, J, plus the determinant of 1, 3, 2, 7, K. Okay, so this is going to be -15 minus 28. I. Minus, this is going to be -5 minus 8. J. Okay, and this is going to be 7 minus 6. K. Okay, and so we're going to get -43I plus 13J plus 1K. Okay, and so what's the vector? What's the cross product? It's -43, okay, 13 and 1. Okay, that's A cross B. Okay, two non-zero vectors. Two non-zero vectors are parallel if and only if A cross B is equal to 0. Okay, if and only if the cross product is 0, then they're parallel. Okay. So if the cross product is 0, then they're parallel. Okay. So if I have a vector here, A, and I have a vector here, B, make it a different vector, B, if the cross product of those is, the cross product is 0, okay, then they're parallel. Okay. Okay. So then they're parallel vectors. They don't intersect. Okay. So it just means that A is a scalar multiple of B. That's all this means, is that A is a scalar multiple of B. And I will put vectors here to differentiate between vectors and scalars here. Okay, and if you really want me to, I can bold these for you. Okay, A is just a scalar multiple of B. Okay, and so when I do the cross product here, I just end up with 0 because a bunch of stuff will cancel out. Okay, so the cross product is 0. Okay, so the magnitude, okay, the magnitude of A cross B, the magnitude of A cross B is equal to A, B times the sine of theta this time, right? So the magnitude of A cross B, it's not A cross B. Remember, the dot product was A dot B, but this is the magnitude of A cross B. Now, why is it the magnitude of A cross B? Because it is, okay, then the angle between the two is the sine function. Okay. So if the angle between the two is the sine function, then the magnitude of the cross product is 0. Does that make sense? Well, what's the sine of 0? What's the sine of 0? What's the sine of 0 degrees? Isn't that 0? So wouldn't this tell me that the magnitude of A cross B, or A cross B, would have to be equal to 0 if the angle between them was 0? Does that make sense? We kind of get this backwards. We just say, hey, the angle between them is 0. Therefore, the magnitude of the orthogonal cross product is also 0. Oh, okay. It's kind of just an intuitive proof. I'm not going to go into a formal proof on this one. Okay. But then, you know, recall that A dot B, which is a scalar, this is now a scalar. This is a scalar. All right. Why is it a scalar? Because we're taking the magnitude of it. Does that make sense? The magnitude of it. Yeah. Scalar. Okay. And so remember, A dot B was equal to magnitude A, magnitude B, cosine theta. Right? So that's A dot B. Okay. Okay, let's talk about some properties here. What time do we go to? 45 after, is that right? 45? No? What time do we go to? Yeah, 45 after. Yeah. Okay, so we got a half hour, that's good. Okay, some properties of cross product. Oops. Go back. Okay, properties of cross product. Okay, so number 1, A cross B is not equal to B cross A. This is not commutative. B cross A, this is not commutative. Okay, it's not commutative. Okay. Okay. Okay, A cross B does equal, however, does equal negative B cross A. Okay, it's negative B cross A. It's kind of interesting. Okay, M times C, let's see what happens if we get a scalar here. M times A, okay, M times A, and again, A and B are vectors, M is a scalar. So you want me to write that? A is a vector, B is a vector, M is a scalar. Okay, A is a vector, B is a vector, and M is a scalar. I can't sit there and switch to bold all the time, but I'll just go like this, okay? M is a vector, A is a vector, M is a scalar. Okay? M times A cross B, okay, is the same as M times A cross B, okay, which is equal to A cross M times B. So basically, you get basically just factor out the M is all it's saying. Okay, the scalar is factorable is all this is saying. Just factor it out. Okay, pull it out in front if you really want to. Okay, so what about this guy here? Okay, number 4. Okay, A cross B plus C. Okay, so we got 3 vectors here, A, B, and C. Okay, A, B, and C. C is a vector. C is a vector. Okay. Okay, this is equal to A cross B plus A cross C. So this is kind of like the distributive property for cross product. Okay. But you can't do crossings. That's not going to work. Okay, crossing is not going to. That's going to be a whole different thing. Okay. So number 5. Luis, can you turn your mic off? Thanks. Okay, number 5. Okay, A dotted with B cross C. Now we're doing a dot product with a cross product. Okay, this is the same. It's kind of weird. It's the same as A cross B dotted with C. That's interesting. That's kind of a weird property. Okay. Okay, and then number 6 here. Number 6. Okay, is that A cross B cross C. Now what happens when I cross across? Do a cross product of a cross product. Well, this is kind of interesting. It becomes A dot B times, or sorry, A dot C, dot product of A dot C times vector B minus A dot B times vector C. Okay, where A dot C is this is a scalar, right? This is a scalar times a vector minus a scalar times a vector will give us a vector. It's a vector out. Okay, so those are the properties there. Okay, let's look at the volume of something called a parallel pipette. I'm like, what the hell is a parallel pipette? I'm like, well, I'm glad you asked. Okay, a parallel pipette. Okay, this is a box squash. This is a squash box. Like, what do you mean by a squashed box? Okay, so let me try to draw this as best as I can. I'm gonna break the ruler out on this one because I don't trust my drawings. Okay. Let's do this guy here. Okay. Let's flip this guy 90 degrees. Okay. Let's make it now a 70-degree angle. $70, please. Come on. There we go. 70-degree angle here. Okay, I'm going to have another 70-degree angle down here. Okay, maybe I should have let these be axes. I'm gonna get rid of this one. Okay, what color do you want? What would be a good color for a parallel pipette? How about, I don't know, what's this color over here? Ocean? Ocean. Let's do ocean. That's kind of cool. Okay. Ocean's parallel pipette. As opposed to Ocean's 11. Okay, so let's do ocean here for our parallel pipette. There's one. Okay, I'm going to move this over. How long was that? A little over an inch and like an inch and 3/8, an inch and 3/8. So this guy is going to be an inch and 3/8 as well. Right there. Okay. Okay. Now let's go at, I don't know, 35-degree angle. That'd be good. Kind of cut it in half. Sure. Let's do a 35-degree angle. Let's make this an inch. Let's make that an inch. Okay, let's do the same over here. 35-degree angle, make that an inch. Nice. Bring this down. Do that as well. Okay, bring that down here as well. Okay. Good, that's good. Okay, I'm going to connect these 0 degrees. I'm going to connect these at 0 degrees. I'm going to connect these 0 degrees. Okay, and then I'm going to go up and just connect these. Hopefully at 70 degrees. Okay. And what is that? That, my friends, is my parallel pipette. Okay, that's a parallel pipette right there. Okay, make sense? It's kind of like a box, but it's squashed. Is that good? Okay. So let's take this and make this our x-axis, 35 degrees. Okay. And this guy's going to be my y-axis here as well. Okay, and then obviously the one that's going up at 90 degrees is my z-axis, right? It's going to be y, x, and z. Okay. Okay. So I claim that the volume of the parallel pipe head is equal to, okay, this volume is equal to, that's my claim. My claim is that it's equal to, okay, vector, okay, vectors A, this is equal to the magnitude of vector A dot B cross C. That's my claim here. Okay, is A dot B cross C. Now, what's A, B, and C? Let's label these. Okay. So, make sure I get this correct. Yeah, this is A. Let's label these in black. This is A. This is B. And this is C. Yeah. Okay, so this is vector C. This is vector B. And this is vector A. Okay. Okay. So the volume is the magnitude of this guy dotted with the B cross C dotted with A. Okay, B cross C dotted with A, and the magnitude of that is going to be the volume. Let's see why this is. Okay, let's look at our parallel pipette and see why this is. Okay, so what's the volume of a three-dimensional figure here? Well, right, when we think about a parallelogram, how do we find the area of a parallelogram? Isn't this base times height? Right? Isn't that base times height? Okay, the area of a parallelogram. So I could say that the base area is equal to B times H. Does that make sense? The base area here, the base area is B here, the base area. That's this area here. That's B. Does that make sense? The base area. Okay, but now how am I going to find the volume? Well, couldn't I find the height of my parallel pipette? Couldn't I find the height of that? Okay, so the height of my parallel pipette, how am I going to find that? Well, that's this guy here, right here, right? That's the height, right? So we'll call this H for the height, or maybe capital H. We'll call it capital H, because we're calling this capital B. Okay, so the height there, okay, so the volume is going to be B base area times H. Does that make sense? The base area times H. Okay. So how can we find the base area here? Oh, okay. Well, we need to figure out what B is first. What's the base area here? Well, what did we say? We said that this guy was vector B, and this guy was vector C, right? Vector B and vector C. How could I find H here, little h? How could I find little h based on vectors B and vectors C? Well, can't I say that this is angle theta? Couldn't I say that that's angle theta? Remember, this is the base. Isn't that angle theta? And so how would I find H? Isn't H just, Well, isn't the sine of theta equal to h over c? Does that make sense? And again, these are magnitudes. This is the magnitude of c. Right? Does that make sense? That's the length of c. It would be the h over the magnitude of c. So what would h be? Wouldn't h be equal to the magnitude of c times the sine of theta? Does that make sense? Times what? Times the magnitude of b. Right? So this would be the magnitude of b times the magnitude of h. Right? So the magnitude of b times, so the base area would be the magnitude of h times the magnitude of c, I'm sorry, the magnitude of b. Stop, erase. Why is my eraser not working? Go back to the erasing. There we go. Okay. So it's the magnitude of b times the magnitude of c times the sine of theta. But we saw we had something for that before. What was that? What was that equal to? What was that equal to?
A dot B.
This is
B cross C.
B.
It's B cross C.
It's b. It's the magnitude of b cross c. Does that make sense? Isn't that the magnitude of b cross c? So the magnitude of b cross c is b c sine of theta, which is the area of a parallelogram
A's.
with sides b, vector b and vector c, right? Does that make sense? Okay, so the area of a parallelogram, right? So what would be the area of a triangle? What would be the area of a triangle? If I had vector b and c, how could I find the area of the triangle created by those two vectors? Wouldn't that just be half the area of the parallelogram? Does that make sense? That would be half the area of the parallelogram. Oh, okay. So the area of the triangle is 1/2 b c sine of theta, which is 1/2 the magnitude of b cross c. That's the area of the triangle. Okay, we don't want the area of the triangle. We do want the area of the parallelogram, which is this guy here, right? So we have this guy here, and we're going to use that guy. That's the idea here. Okay, but the area of a triangle that could come in handy later on. I'm gonna box that one too. That's a nice handy one there. Okay, and yes, these are vectors. There you go. Hallelujah. Okay, so now what are we gonna do? Well, we're gonna take this guy from over here, and we're gonna put him in here. Oh, okay. So actually, what I'm gonna do is I'm gonna say that b is equal to this guy here. Now let's just put that in there for right now. B cross c, the magnitude of b cross c. Okay, so the magnitude of b cross c. Okay, nice. Now what's h going to be? What's h going to be? Okay, this is times h, not dotted. It's times h. So
A times cosine of theta of the angle.
yeah, exactly. Look at this. Look what's h? H is, if we put in an angle here, say phi, that's the angle that's being made with h and a, right? If we make that angle phi,
It's A times, oh, it's the sine of the thing, right? A times sine of,
no, cosine,
okay, cosine of, yeah, cosine of the angle.
right? Because isn't it adjacent over hypotenuse? right? Adjacent is h over hypotenuse. Okay, so we can say that h is equal to, right? Or the cosine of phi here, the cosine of phi is equal to, okay, cosine of phi is equal to, maybe I'll just do this. It's getting too garbled. Okay, the cosine of phi is equal to h over, right, h over the magnitude of a. Does it make sense? So far, so good? Okay, cool. Okay, so what is h? Isn't h the magnitude of a times cosine of phi? Yeah. But, and what was b? B was the magnitude of b cross c. Okay. So we've got v is equal to, let's plug this all in. V is equal to the angle b cross c, or the magnitude of b cross c, times the magnitude of a, okay, times the cosine of phi. Now, what is b cross c? In what direction is b cross c? What's the direction that b cross c takes? B cross c, isn't that in the direction of h? Isn't b cross c orthogonal? Isn't it going to be a right angle? What the heck, man? Go away. Stop. Go away. There we go. Okay. Does that make sense? That let me zoom in here. Okay, let me zoom in on my image. Okay, does it make sense that when I do b cross c, that this thing is going to make an orthogonal to this plane, to this xy plane? Does that make sense? It's going to go b cross c, and again, right-hand rule, b cross c is going to go perpendicular, and so isn't that going to be in the same direction as h? Does that make sense? So b cross c, okay, is b cross c is in the same direction as h. It is h, basically, you know, and this it's not going to be h, it's going to be in the same direction as h. It's going to be in the same, it's going to be a scalar multiple of h. So the magnitude a cross b, the magnitude of a cross b is equal to a scalar multiple of h. Right? It's going to be in the same direction, okay, as the height. So what this means is this. Let's tie this all together. What this means is that when I take b cross c, which is in the same direction as h, right? As h, that's the magnitude of that, the magnitude of b cross c, right? That's in the same direction as h. Well, with a and the magnitude of a, and then I take the cosine of phi. Well, isn't phi the angle between a and b cross c? Isn't phi the angle between a and b cross c? Yeah, look at this. The angle between a and h is phi. Well, wouldn't that be any angle that's a scalar multiple of h? Wouldn't that be the angle between a and any scalar multiple of h? Because the angle doesn't change, it's just the magnitude or the length of h changes. Oh, okay, that's kind of cool. Because now what is this? Well, this thing is now the dot product. You're like, what? Yeah, this is dot product. This is now the magnitude of a right? Right? Times B cross C, cosine of the angle between the two, is equal to A dot B cross C, the magnitude of those. Crazy. Okay, it's the magnitude of that. Okay. And so that's the volume there of my parallel pipette. I want to talk about one last thing. Okay, one last thing, and that's torque. Okay, torque. Okay, torque, the magnitude of torque, okay, is the cross product of the length vector and a force. Okay, is the cross product of the length vector, we'll call this R, the length vector and the force. Okay, so torque, the magnitude of the torque, is equal to the magnitude of the length times the magnitude of the force times the sine of theta. Oh, okay. Where theta is the angle between the applied force, okay, and the length vector. Okay, so this is length, and this is force. Okay, the length times the force times the sine of theta. Okay, that's going to give me torque. Now, okay, let's say that we have a wrench. Okay, I'm going to draw a wrench, which is not going to look good. So just, if you don't like my wrench, well, forget you. Okay, here's my wrench, right? Okay, and we'll try to draw a hexagon, but all bets are off. Okay, so there's my nut. Okay, so I'm gonna wrench this thing, right? I'm gonna torque it. Okay, not torque it, torque it. Okay. Okay, so this is 0.25. The length here is 0.25 meters. That's the length. The length is 0.25 meters. Okay, and I'm going to apply. Okay, I'm going to apply the. I'm going to apply. I keep saying the same thing, but it's true. I'm going to apply the force, okay, at a 70-degree angle. I'm going to apply the force that is, I'm not coming at it completely orthogonally, okay? I'm coming at it at a 70-degree angle. Or let's actually make this 75 degrees. 75-degree angles, okay? So what's the torque that I'm torquing this thing at? Well, the torque is going to be, okay, what did I say? How many newtons? How many newtons of force? 40 newtons. Let's do 40 newtons. Okay, so this is 40 newtons. Okay, so 40 newtons. Okay, so the magnitude of the length is 0.25, rotational radius, right? That's why we call it R, because it's radius. Rotation radius is 0.25 times the force that I'm being applied is 40 newtons times the sine, right? Times the sine of 75 degrees. Okay, times the sine of 70, that's the angle at which it's being applied. Okay, if the angle is, whatever, we'll talk about that later. I think I drew the picture wrong. I think the angle should be here. Because an angle of 90 degrees should just give me 1. So what's the sine? Or yeah, the sine of 90 is 1, right? The sine of 90, a 90-degree angle should be 1. Okay, a 90-degree angle should be 1. An angle of 0 degrees should be an angle of 0 degrees. So it's this angle here. I think I drew the wrong angle. It's this angle here. An angle of 0 degrees should give me nothing. If I apply force to the top here, it's counterproductive. Okay. If I get the whole force, it's when it's 90 degrees, when it's orthogonal to the wrench, right? If I push the wrench orthogonally, boom, I get the maximum amount of torque. So it's this angle here, theta. Okay, so yeah, exactly. Okay, so this is just going to be torque is approximately 9.66 joules of force. It's Newton meters, right? Force times distance. Okay, 9.66 joules. Okay. Okay, so you get the idea. And then where the force is coming in at 40 newtons. Okay, we'll stop there for today. Okay, my office hours are in 10 minutes. If you have any questions, let me know. Is anybody going to show up for office hours? Let me know now. Anybody have any questions on anything?
Yeah, I have questions.
Okay, so I'll be there in 10 minutes, okay?
So is it on the link to Zoom or?
Yeah, it's on ConferZoom. It's the same, it's how you got into this place to begin with. Okay? Same place. You're welcome, Vanessa. Thank you as well.